So what we're going to do up here at the top is we're going to use the graphing calculator to graph these quadratics. Then we're just going to sketch them. So let's get to good old y equals here. We definitely do not want the radical that's already there. And we're basically right now just going to play a little, and we're going to type in exactly what we see. So the 0.25, if it's been a while, this button next to alpha here, the xt theta n, that's our x button. And then squared is kind of halfway down the left side here. So when I'm ready to graph, of course, I'm just going to hit graph. Now, when it says accurately sketch, stressing the word accurately, okay, I don't want to just kind of half-heartedly go, okay, I'm good. No, because the little things we're going to start to see from these values are going to be important. So to get very accurate and not have to do this all with mental calculations, if you hit second and graph, you'll get this handy-dandy little table here. You're like, well, how many numbers do I want to use? Well, in this case, I think it would be appropriate for us to do several. So I'm going to start at 0, 0 here. That's my safest point. And then as long as you do a couple at least each way, that's okay. I mean, the more we do, the more accurate it's going to be. And you're like, ooh, decimal's fun. So again, we're just going up a very little bit on each side at 1 and -1. And then at 2, 1 and -2, 1. And what you'll notice is, and I put 0, 0 in the middle of my chart for a reason, if you look at those, you're like, hey, it looks like the exact same numbers on each side as I go up or I go down. As I get 1 away from the middle, you know, they're both 0.25. They're both 1. They're both 2.25. That's going to be something important as we move forward, because that's going to help you find where the vertex of your parabola is going to be. So whenever I can find those reciprocals, okay, those opposites, kind of our mirror images, that's going to help me out. So go ahead. And again, these are curves. These aren't absolute value equations. I don't want V's. Okay, as long as you get a little curve in there, you're okay. Make sure I get my arrows on there. So as you start to see some of these, is my calculator turned off? Yes, sir. I do. So what we'll do is you can either leave the last one on, or we can even get ourselves a couple going at the same time here. That might be interesting as we go along. I'm going to wipe mine out here. Remember, this time I got a negative that I'm working with. Except I don't want double negative. That would be bad. There we go. So -1/2, and again, my x is just next to alpha, and my squared's about halfway down there. So let's see. Well, we're noticing a couple of things, hopefully. We notice, first of all, that now it's opening downward. And you may or may not be able to notice at this point that it's starting to not be quite so wide. We're going to take a look at that in a minute here. But again, if you use second and graph to get your table, again, you'll notice that 0, 0 seems in the middle because it's symmetrical on both sides of that. Now, I'm not one of those that typically says we absolutely have to draw a chart for everything that we do. I think after a while that can get a little tedious. But there is some benefit in being able to see the values that you're working with. And even if you just look at your own two sketches for graph A and graph B, you'll notice graph B isn't as wide, okay? It's not expanding as much as the first one did. And there's a reason for that. We'll be talking about that here in a bit. Graph C, this is what we call your base graph or your mother graph for quadratics. It's just y equals x squared basically, because we know that if you put 1 in front of something, it really doesn't change the value that much. So if I put that next one in, okay, the C, that's my base graph. And we'll get to a point where we start shifting these around using the values that we have. But we're also going to keep noticing, you're like, these all start at 0 for now, because we're not doing any shifts of any sorts. But again, we're also seeing that that's our central point because we're getting symmetry about that value. And again, we continue to notice that this graph kind of keeps getting skinnier as this number continues to get bigger. So like, for instance, if I change that coefficient to 2, I think it's going to get even skinnier yet, and it does. Because if I compare that to the first one that we did, and I'm just going to put both of them up at once, you'll start to see the one that's skinnier on the inside is actually our 2x squared parabola, whereas the one on the outside is our 1x squared. So let me get that out of there because we're going to get our table going here again. And you notice the numbers start to increase really, really fast. You're like, ooh, it's like -1, 2. What if I can only get, 3 points? Because I don't think I can get 8 on here. 1, 2, 3, 4, 5. I mean, I guess I could wing it and kind of put it, oops, swing over. I could wing it and put it up a little bit higher. But even if you only have the 3 points, it's okay. But the more points we get, of course, the more accurate our graph is going to be as it extends away from our vertex. So now let's kind of see if we can put this together before I even graph the last one. Some of you probably already have. What are a couple things I know about this last graph? Just looking at the expression. Which direction do you think it's going to open? It's going to open down. And is it going to get wider or is it going to get skinnier? It's going to get skinnier. So let's see here. Graph. Yep, skinnier, and it's going downward. And again, this is the nice thing about the calculator. Yes, I could just plug numbers in for x and do mental math and figure all these things out. But occasionally it's nice, I mean, if you know what you're doing, to be able to just sketch a graph as accurately as you can with the size of the graph that you're given and the amount of numbers that you can use. But we just kind of start to see what's happening. So you're like, okay, I mean, that's all fine and dandy. I can sketch something, a graph from the calculator. So what? Well, a couple of things. What do you notice about every one of the graphs? About their shapes? Yeah, they're all curved. They're all either like these U's that are going up or down, and those are called parabolas. And they're always going to be symmetrical in some way. Whether they're wide, whether they're skinny, it doesn't matter. Once we find that central point, we're going to find equal on both sides, just like we stuck a mirror in the middle of them. So let's see here. Under what conditions does the graph of y equals ax squared, which is what these are all in, open upward? What do you notice about all of them that open up? Yeah, they all have a positive a value, and that's just what we call whatever our coefficient is in front of our x squared term. So yeah, whether it was 0.25, 1, or 2, they were all opening upward because they had a positive a value. If they have a negative a value, that's when they're going to open downward, like we saw up in B and E. So that's one piece of the puzzle we can take just from looking at the equation. Now, as the absolute value of A increases, and we say the absolute value, even though you don't see that any of these, is because no matter if it's positive or negative, okay, whether something gets skinnier or widens, it's not the sign that matters, it's just that value, and that's why we talk about the absolute value here. So as it got bigger in value, what happened to my graph? Yeah, it got skinnier, it got thinner. Whatever one of those words you would like to use would work okay. And if it got smaller and smaller, it would get wider and wider. So, now, let's see what other little shifts and things can make little adjustments to our parabolas. So we're going to graph these on here. And we're going to take a look at them together, actually. I'll put them on here one at a time. But I am going to let several of these get graphed on here at once so we can kind of see what's going on. So I'm looking, I'm like, ooh, for the first time my vertex moved. It's not on 0, 0 anymore. I wonder where that is. Let's see. Interesting. Now it's still symmetrical because I can see the numbers go the same as I move up or down with the calculator table, but, and you're like, how the heck am I going to graph this? You didn't give me enough spots. I know. So let's see, 1, 2, 3, 4, 5, 6, 7. We'll get a little creative here. Okay, so there's my letter A, my 3x squared plus 4. Now, keep in mind, when we're doing these, and this is going to be the first time, I'm going to put two of them up here at once, because I want you to be able to see in the table form kind of what the difference is. So if I do 3x squared plus 2, first I'll look at the graph. That makes sense, because it's opening from a spot a little bit lower. Well, my plus 2 is a little bit lower. So if I look at my graph, I look and I'm like, okay, so that y value used to be at 4 for my y-intercept, now it's at 2. But I also notice all of my other values have also shifted down too. Okay, my first y value on each before was 7. Now it's 5. But the width of my parabola hasn't changed. The difference is I'm seeing it from a little further down, so I'm getting a little more accurate of a depiction. Okay, the width shouldn't be changing. So you're like, okay, well, what if we just take that one and I just change it to minus, because that's what the third one's asking me to do. So if I try that out, okay, let's see. I notice my vertex shifted down 2. And if I look at the chart, again, I look, okay, it's down 2. I'm kind of getting the drift here of how this is working. And then I can get my couple more points on here. And again, my width, I'm just seeing more of my parabola. That's why it kind of looks like they're going inside of each other, because parabolas expand as you get further and further away from your vertex. So it may look like sometimes they're kind of growing inside of each other, even though as far as their spacing goes, it would be exactly the same. And then you probably can figure out what's going to happen with the last one here. If I go to minus 4, yeah, it went down a little bit further. So my 0, negative 4 comes down to here. And again, I get my other 2 points at negative 1 on both sides of my So the only thing that changed, it didn't change in width, it didn't get skinnier or fatter. What happened was we basically just did some up and down shifts. So my value of C moves my parabola up and down. You're like, you know, that's kind of like when we were doing the square root graphs, absolute value graphs. Yes, they all have that same type of idea working. So, if you get a question like F or G, life should be fairly simple. So if at what point would the graph of y equals 3x squared minus 8 intersect the y-axis? Think about the ones you just graphed. If you just have that value on the outside, your graph's going to intercept the y-axis at that point. Unless you have some other sort of shift, and we'll talk about that in a bit, that's going to be where my intersect would be. If it's a positive value, again, And you're like, now why are you putting the 0 in there? Why aren't you just saying, you know, y equals 5 or y equals negative 8? Again, an intersect point is a point, okay? It's not a line. Y equals in a number is a line. So I need to put the intercept in there, and we will be doing some x-intercepts too, and that's why it's especially important to put the 0 in the right place. So that would be my intersection point for either of those. So what that's going to lead us into, and we're actually going to start graphing this on the back as we flip, a parabola has a maximum value. So if, like, you're in business, your maximum profit when it opens downward. In other words, if it looks like a hill, that point that's up at the top is my maximum value. It's still going to be the vertex, we just have a specific name for it there. If it opens upward, like a U, my vertex is going to be at the very bottom. That would be my minimum. Like the least amount of money I could make to actually make this worthwhile or something like that. So we can kind of start to see how this works. So we've gone from skinny to wide. We've gone up and down. Well, let's see what other directions we can move here. And if there's ever anything as we're doing these, you're like, well, wait a minute. Why does that, you know, with something? Let me know. I will absolutely be willing to help out with that. Okay, now here comes the fun part. Without using the calculator, indicate whether each of the following equations would open up or down, be wider or narrower, and where the graph will intersect the y-axis, then sketch the graphs. Oh dear. Okay. Which direction is this parabola, once we graph it, going to open for number 3? Down. How do we know that? Yeah, my a value is negative 1/4, so that lets me know it's going to open down. Okay, so speaking of that 1/4, what's that going to do to the width of my graph? Yeah, it's going to be bigger. It's going to be wider. Because anytime we get that value that's fractional, that's between 0 and 1, it's going to get wider. Where are we going to intersect the y-axis at?
5.
Yeah, at 5. And again, we want to keep putting things as coordinate points. So since it's my y-intercept, my 5 will go in the y spot, 0 will always go in my x. So if it opens down, am I going to have a maximum or a minimum? Max, because we're going to be at the top. I'm just going to circle that. And then here's the part maybe we haven't thought about yet. But every one of our graphs, we keep having this intersection and our vertex on the y-axis. When you have an up or down shift like this, there's a direct relationship between where it intersects the y-axis and where your vertex is going to be. Now once it starts to shift left and right, that's a little bit different, but for now, those two things are going to be directly related. So you're like, okay, so now how am I supposed to graph this? And you're telling me don't use a calculator. Well, there's a couple of points I can get that are really going to be easy. One of them always is plugging in 0 because, well, we already know what's going to happen when we plug in 0. It's going to be 0, 5. Now, I personally like to avoid decimals and fractions when I can. So I kind of start looking at this. I'm like, well, if I plug in 1, that's going to be negative 1/4 times 1. I'm not a big fan of that. But if I plug in 2, 2 squared is 4, and negative 1/4 times 4 would be negative 1. Okay, I can do this. So I'm just going to kind of do this for a second. I'm like, okay, 0, 5. 2 seems to be a good number to work with. So 4 times negative 1/4 is negative 1, plus 5 is 4. Okay, so 2, 4. Oh, yeah. And these parabolas are symmetrical. So if I go to the right 2 and it's at 4, if I plug in negative 2, it's also going to be at 4. Because again, whenever I plug a value in, it's in parentheses. So negative 2 parentheses, quantity squared, is still positive 4. And that's a way I can get a fairly accurate graph without going to the calculator. Now, does it mean that I can't go to the calculator and check? No. But I'm just saying, if for some reason you're somewhere sometime and you don't have a calculator, this is kind of a nice option for you. Now, we won't go absolutely crazy and do every single one of these, but I want to do a nice chunk of them so we can kind of see how this is working. So, all right, let's check out number 4 here. Which direction are we going to be opening? Up. Because my A value is positive. Okay. Are we going to get wider, skinnier, what? Skinnier. Because again, my A value is greater. My absolute value of A value is greater than 1. All right, where are we intersecting Y at? 0, -4. Because again, we're not moving left or right at all here, so that makes that simple. And again, I'm going to take care of my vertex with that at the same time. One and the same. And since we're opening up, are we doing a min or a max? It's a min. And again, that's true every time. If it opens down, it's a max. If it opens up, it's a min. That'll never change. So I'll plot my vertex. And this time it doesn't look like there's going to be a whole lot of craziness no matter what value. So let's say I even use 1 here. And again, you don't have to write the chart. That's not a necessity with me. But even if you just have 3 points, 1 squared would be 1. So 5 minus 4 is 1. And again, it's going to be symmetrical. And we notice that got a lot skinnier, especially compared to number 3. But again, as long as you get 3 points, you're good. We'll keep something that's kind of nice. All right, a couple last ones here. Take a look at 5. All right, I'm just going to roll the questions. Open up or down? Down. Because my A value would be -1 on this one. What about my width? Yeah, it doesn't do anything. It's basically what the base is going to be. So I guess we'll just call it the same, or you could call it the same as the base. Unless you have some sort of a coefficient besides negative or positive 1, it doesn't do much. So where are we going to be intersecting the y-axis at? 0, 3. Which is also going to be my vertex. And since we're opening down, what are we going to have? A max or a min? A max. And again, with just having a negative coefficient in front, it makes it kind of easy for me when it comes to dealing with the numbers. When given the choice, I'll just keep doing -1 and 1. But be careful, because again, you've got the negative out front. So even if you do 1 squared is 1, it still ends up being -1 because of that. So -1 plus 3 would be 2. And that takes care of those. We've got basically a base graph that's been flipped upside down here. All right, one last one. I want to look at number 6. I want to deal with another one of these fraction ones. Because fractions are just part of life, especially in this class. All right, let's see what we got to play with here. Y equals 1/3 x squared minus 1. All right, what direction are we opening in? Up. Our width. What's going to happen with that 1/3? It's going to get wider. Where's my y-axis going to get intersected and also my vertex? 0, -1. And since we're opening up, it's a min. Now again, try to do something that's going to keep life simple. Again, if I plug in 1, I got to deal with the decimal or a fraction. If I plug in 2, I got to deal with the decimal or a fraction. Not that that's the worst thing ever. But if I punch in 3, 3 squared is 9. 1/3 of 3, 1/3 of 3, holy cow. 1/3 of 9 is 3, minus 1 is 2. So you're like, oh, and that kind of goes along with, because up there I was dealing, with a multiple of 2. Oh, I kind of see how this is working now. There's our wide going. Okay. And that's, again, how those work. Now, again, this is, again, taking for granted. We're not doing left or right shifting. We're not doing anything else. But if it's a straight base graph, that works out pretty well for us. Now, we're going to get a small start into some other things we can do with these equations. So we're going to get just a bit of a start into this other packet. And like I said, we're going to do a bigger chunk of this tomorrow, but I just want to do a little bit on the front here and then try to stay away from overload. Okay, so quadratic functions. This is our base form. Okay, ax squared plus bx plus c. And a, b, and c are just numbers that are in front of our variable terms. Now, write each function in the form. So basically, if you get one that's looks like this instead, we're going to FOIL this out, combine like terms, and then we're going to base everything off of that. So I'm always going to keep talking about this as f of x. You might see it as y equals sometime. And basically, I'm going to FOIL this guy out. And combine like terms. Because then it's going to look a little more like our form that we're talking about up here, our ax squared plus bx plus c. I have a squared term, a non-squared term, and a constant term. But the one other thing they're talking about is this a, b, and c. So we're going to have some formulas that we're going to use based on those numbers. But they just go right in order as well. My x squared coefficient is going to be my a. My x coefficient will be my b. And my constant term will be c. So basically, we just FOILed that out so we could get that information in case we needed it for something else. But again, that's going to happen sometimes with these. So for any of these, again, I'm just FOILing them out. This time I'm going to combine right away. So let's see. So I have 12x and 1x would be 13x. And 1 times 6 is 6. To get into my standard form. And then to find a, b, and c, again, I'm taking my x squared term as my a, my x term is my b, and my constant term is going to be c. And the only reason I would really talk about number 3 a whole lot is sometimes the temptation is there to just distribute that 2 through and call it 16x squared plus 1 and call it a day, but that won't quite work. Because remember, 4x minus 1 squared means I've got 2 of these. And if I don't write it out and FOIL it, or FOIL it with the square in my head, I'm going to end up missing my middle term. Because here, so there's my 16x squared. I was expecting that. But remember, here I've got minus 4x and another minus 4x. So minus 8x, they do not cancel. And then negative times negative is positive. So there's my standard form. And I can get my a, b, and c values. Now, just because they're written in a factored out form like that doesn't mean the shape that they take on would be any different. So for instance, let me come back to the calculator for a minute. If I were to type in exactly what I saw here, I'm not going to FOIL it out, I'm not going to do anything fancy, I'm just literally going to type in my 2 quantities. If I go ahead and graph it, you're like, I still end up with a parabola, I still end up with a quadratic. And that's going to be true for any of these. So basically, what I'm trying to show you with this section is that you are going to get quadratics or parabolas for all of these, okay? So they're all parabolas slash, if we want to get very mathematical, they're all quadratics. So if I were to FOIL these out, to multiply them out, because I wanted to see them in their standard form, and I'll just do these for you because I know we've done enough foiling. We don't need to go FOIL crazy. We don't need overkill here. Because what I basically, all I want you to see from this, they may not all look exactly the same. You may have a coefficient in front of x squared, you may not. You may not even have 3 terms. But notice the highest exponent for each one is 2. That's what makes them quadratics. That's what makes them all look like parabolas, those U-shapes, is the fact that they each have a highest degree of 2. So, they're like, oh. Like we'd mentioned up above, all of these, even if they're in their factored out form, could be FOILed out to written as ax squared plus bx plus c, which is our standard form. So the last thing I'm going to talk about today, and then let your brains kind of recover here for a little bit, because we've talked about a lot of this down here. If my a value is greater than 0, in other words, it's positive, my graph opens up, and the vertex is the lowest point. And we talked about when it opens up and we're at the lowest point, that's a min, or a minimum. If that a value is less than 0, fancy way of saying it's negative, the graph opens down, my vertex is the highest point, and makes it a maximum. So, just for our last little simple thing here at the bottom, and it actually is, we talked about vertex. We haven't talked about this thing called the axis of symmetry yet, and basically what that would be, if you wanted to get a kind of a picture of it, if I were to take one of my graphs, take my paper and fold it in half, okay? Fold it right along where that point is. What would end up happening when I folded my paper, if you can see my fold here a little, is that I have symmetry on both sides. Well, this axis that's causing that symmetry is called the axis of symmetry, and here's how that's going to work. It's always going to be a line through my parabola that divides it into 2 congruent parts. In other words, that symmetry also shows congruency. And just as a little helper for my axis of symmetry, it's always going to be x equals in some number, because you'll notice the line goes vertically, which makes it x equals. And what we're going to end up doing is we're going to use this little recipe that we call it in here to figure out the value of my vertex, because it's not always going to be at 0 something. So last little mini thing. If I know my a, b, and c values, I can use my vertex recipe to find my x value. So all I would do here is I'd say, okay, so it's negative b, or negative 1, over 2 times a. You're like, ooh, that's a fraction. Yes. Once you find that x value, that's your axis of symmetry. Okay, that would be the x value of the line that I would need to fold down to get equality on both sides. You're like, but how do I get y then? Because I just have x. We're going to plug x into the expression and we're going to be done. This is the part that gets a little ugly. So you're like, so I got to plug -1/2 in there? Yeah. So -1/2 squared plus -1/2 minus 6. And again, do it mentally, do it with the calculator. I don't care. So let's just do it this way because it might be a little easier. 1/2 is -0.5. That's what I'm going to use just because it goes a little faster. Make sure I typed everything in right. Looking good. You're like, ew. So my vertex would be -1/2. That was my x value. -6.25 or -6 1/4. Yeah. So the vertices, as you'll see moving forward, aren't always going to be nice and neat, but it is a way for us to be able to get the values. Okay? And like I said, as far as the homework sheet goes, there are a few problems at the very start that you could get a little bit of a head start on. There's some things in there with the vertex, finding the vertex, doing some quick sketches. That'd be okay. But we're going to knock out the rest of this note packet tomorrow, which won't take the entire class like it basically did today. And then you'll have the rest of the time to kind of work on that, and then we'll be working some more on that heading into Wednesday and Thursday. Okay? So that's where we're at.